Hey class, welcome back. This is the last lecture for the semester. We're wrapping up acids and bases today. And we're picking up where we left off, where we were talking about the self-ionization of water. And essentially in pure water, what ends up happening is, and I just drew a little picture down here so you could see it. This is the overall reaction, but I'll show you exactly what's going on down here. If you remember, the hydrogen on each water molecule, every hydrogen has a slight positive charge and every oxygen has a slight negative charge. So essentially what happens is that when two water molecules come in contact with each other, since there are so many in pure water, statistically what happens is that the slight negative charge on the oxygen is attracted to the slight positive charge on hydrogen, right? And essentially this hydrogen molecule, or this hydrogen atom, right here, pops off. So the oxygen right here keeps the electrons from the bond, the hydrogen pops off, and my notability is acting up. I don't really know why. And what ends up happening is we end up forming H3O plus. Right, well, one of those, the third hydrogen comes from an adjacent water molecule, and then we also end up forming, because this guy over here lost this proton but kept the electrons, we're going to have OH minus. Remember, we're going to have 1, 2, 3, 4, 5, 6. So basically, in pure water, for every single hydronium ion that is formed, a hydroxide ion is also formed. So in pure water, the concentration of H3O plus is equal to the concentration of OH minus, which is equal to 1.0 times 10 to the negative 7 molarity. All right, that's a very, very, very small amount. And so even though it is a small amount, there's an equation that relates the concentration of H3O plus to that of OH minus, and essentially it's this Kw. This is the proportionality constant. And that guy's equal to 1.0 times 10 to the negative 14. So if you were to plug in 1.0 times 10 to the negative 14 here, and in pure water, you would have the H3O plus concentration would be equal to 1.0 times 10 to the negative 7, and then the hydroxide concentration, again, would be equal to 1.0 times 10 to the negative 7. That's in pure water. Now, what we'll do is we will start to look at how does the concentration of H3O plus and the concentration of OH minus, right, how is that affected in solutions? How is that affected when we add acids and bases to solutions? So again, remember, water always contains some amount of the hydronium ions, the H3O plus. And then therefore, since it always contains some amount of H3O plus, it's always going to contain the same amounts of OH minus. This is a neutral solution. All right? The number of H3O ions equals the number of H3O plus ions equals the number of OH minus ions. When we add acid to a solution, remember what acid does? Acids generate H plus, they're proton donors. So if we add acids to a solution, we're adding H plus to here, and when we add H plus, we're generating more hydronium ions. So in acidic solutions, the number of hydronium ions is greater than the number of hydroxide ions. And likewise, when we add a base, remember specifically bases, or we should Arrhenius bases, right? Those guys generate OH minus, all right? So when we add bases to a solution, the number of hydroxide ions is going to be greater than that of the hydronium ions, and that's what makes the solution basic. So how does the concentration of H3O plus and the concentration of OH minus differ in terms of acidic, neutral, and basic solutions? This is essentially what I just said earlier. In the middle, right, the concentration of H3O plus is equal to the concentration of OH minus, and this is neutral, all right? This is concentration moles per liter. This is times 10 to the negative 7. This is in neutral. We can tip the scales in either direction to make the solution acidic or basic. If we go to the left and we add more H3O plus ions, all right, by adding a base, again, you can see here the concentration of H3O plus is greater than OH minus, and if we go all the way over here, if we add hydroxide anions from a base, that's going to kick up the concentration of OH minus. H3O plus is going to go down, and since we have a greater concentration of OH minus to that of H3O plus, the solution is basic. So how can you use KW in calculations? Just basic algebra, right? If we know that KW is always equal to 1.0 times 10 to the negative 14, right? Then we can, and we're given the concentration of, let's say, OH minus, we can find the concentration of H3O plus and vice versa. And that's all because we know that KW is equal to the concentration of H3O, H3O plus multiplied by the concentration of OH minus, right? And remember, KW is always going to be equal to 1.0 times 10 to the negative 14. Okay, so we can use this to calculate all sorts of concentrations. So what is the molarity of a hydroxide ion in a solution that has H3O plus equal to 1.0 times 10 to the negative 5? So again, if we know KW, which we do, make sure this is KW here. Okay, KW is 1.0 times 10 to the negative 14. Again, that's what I wrote right here. And we have the concentration of H3O plus is equal to 1.0 times 10 to the negative 5. We can rearrange and solve for OH minus. We can rearrange this equation up here. So all we have to do is just say that KW over the concentration of H3O plus is equal to concentration of OH minus. So plugging that in a little bit further, I'm going to zoom in. We can actually just do this in our head, right? So KW is 1.0 times 10 to the negative 14. And our concentration of H3O plus is 1.0 times 10 to the negative 5. When we're dividing by exponents, we're subtracting. So if we're subtracting a negative 5, right, we're going to put, sorry, I'm messing this up. This is going to be, I'm going to throw this down here. So that's going to be equal to 1.0 so it'll be 1.0 times 10 to the negative, looks like, let's say 19, right? Because we're yeah. Let me just double check and make sure my brain was not working today. It's been a long weekend. It's so funny with these exponent rules too. I teach them and then they just go, yeah. 1, 2, 3, 4. Oh, yeah, not negative 9. There we go. I didn't mean 19, I meant negative 9. There we go. So again, so all we have to do is rearrange, right, and solve for our unknown variable. So anytime you're going to be using KW, anytime you have to solve for concentration of hydroxide versus hydronium ions, you're going to use KW, this proportionality constant, you're going to use this equation right here, and you're always going to have KW is going to be equal to 1.0 times 10 to the negative 14, okay? So this is actually a good segue into understanding pH, because pH is another way, or it's a way to describe or understand the concentration. Specifically, it's the concentration of hydronium ions. So specifically, it's the concentration of H3O+. Okay, that's what pH is. It is relevant to H3O+, not OH-. We use pH to describe, even though it just specifically describes the concentration of H3O+, we can use it to describe how acidic or basic a solution is. So most solutions have a pH in the range of between 0 and 14. pHs lower than 7 are acidic. Again, this is more hydronium ions. Greater than 7 are basic because of the more hydroxide ions. And a neutral pH is at 7, and that is where hydronium ions equals the concentration of hydroxide ions. And here you can see the scale right here. Strongly acidic, HCl. Apparently your stomach acid has a pH of 1 to 3, somewhere around there. And then we start still pretty acidic, right? 2, 3, 4, 5, lemon juice, vinegar, wine, grapes, orange juice, rain. Milk starts to get a little bit more neutral. Finally, we have pure water at a pH of 7. And then when we start going more basic, right, 8, 9, 10, we start increasing basicity. And then our most basic is at 14, and that's 1 molar sodium hydroxide. 13 is drain cleaner. So take home messages for this scale is understanding what's neutral, what's acidic, and what's basic. So we can use pH in a calculation very easily. I like these pH calculations. They are, so if you were given the concentration of H3O+, you can calculate the pH of a solution by taking the negative log of that number. You can also do the same thing with the hydroxide anion concentration by taking the negative log of the concentration. That'll give you this thing called POH. But for this class, we're going to look at pH specifically because that's something that's more widely used. But POH is a thing. It is related to the concentration of hydroxide anions, and you guys will dive a little bit deeper into that, into POH in Chem 200. So again, I said that the pH is equal to the negative log of H3O+. So what is a log? A logarithm is a mathematic operator. It means to give to the power of 10. We make pH on a logarithmic scale because we want a more intuitive scale. Having a concentration of 3.0 times 10 to the negative, 7 isn't necessarily intuitive. But if you have something that's like, oh, it's a pH of 4 on a scale between 0 and 14, you can easily just understand what that means right off the bat. So that's why we convert, especially for the hydronium ion concentrations, that is why we convert from just straight concentration. We take the log of it to get pH, because pH, this allows us to evaluate the concentration on a more intuitive scale. You'll see what I mean in a second. So again, logarithms are mathematical operators. It means to give the power of 10. So if you have log 100, that means log 10 raised to the 2. All right, so which would equal 2. If you have log 10, that's log 10 raised to 1, so that will give you 1. If you have log 0.001, right, 1/1000th, that's going to give you log 10 raised to the negative 3, which is going to give you negative 3 right here. For numbers between powers of 10, we use a log table or a calculator. So again, there's no way for you to easily say, oh, what the log of 37 is. Okay? But for log 100, because you know that 100 is 10 raised to the 2, and if a log is a power of 10, then it's just going to be 2. Okay? I would really highly suggest you finding out where the logarithm button is on your calculator in order to do these problems. Okay, so here's a sample calculation. What is the pH of a solution with a concentration, remember this is still hydronium ion, H3O+, right, of 10 to the negative 5. And again, this is the same thing as saying 1.0 times 10 to the negative 5. Okay? So what is the pH? All right, what is the pH? If I asked you what is the concentration of OH minus, you would have to take this number and plug it into Kw, just to have you remember this. Okay, you would have to plug this number into this, and we know that Kw is 1.0 times 10 to the negative 14. So you plug that in here, and you will rearrange and solve for OH minus. This question is asking, we know the concentration of H3O+, and so can you give me the pH of the solution? And the answer is yes. So all you have to do is take 1.0 times 10 to the negative 5 molarity and plug it into here, negative log, right? So basically, if it's the negative log of this is going to be negative 5 anyway, and then the negative of a negative is a positive, so the pH of this is 5. And it would be, because it is below 7, it's going to be weakly acidic. So again, this brings us back to the pH scale. Each number on the pH scale represents a factor of 10, and that is again because it's a logarithmic scale. So if you have a pH of 3, and then you compare that to a pH of 4, the pH of 3 has 10 times more hydronium ions than a solution of pH 4. Okay. So how does a solution of pH 3 compare to pH 5? It's going to be 100 times, right? So if 4 is 10 times more, 5 is going to be another 10 times more. Okay. A solution of 9 has a pH, so just to make sure that you guys also remember, if we have a solution that is lower, if we're comparing two solutions, the solution that has a lower pH is going to have more hydronium ions. But if we're looking at a solution that has a pH of 9, and we compare that to a solution of pH of 10, you can look at it and say it has 10 times more hydronium ions than a solution of pH of 8. Okay? So how does a solution of pH of 9 compared to the solution of pH of 7? Again, it's going to be the same thing up here, but in terms of hydronium ions. So here's the scale right here. Here is the actual molarity, right? And again, this is all based on the concentration of hydronium ions. So as we increase, so concentrated HCl is given at a pH of a -1 roughly. Battery acid is at 0. And then as we increase the hydronium ion concentration, decrease the hydronium ion concentration, our pH increases until we get to neutral. And then you'll sit back and then you'll start to notice that as we go down to 10 to the negative 14, all right, that's a very small number. It's a very small number. So if we have something that is 10 to the 14 or 10 to the 13, if it's 10 to the negative 13, then our OH minus has to be equal to 10 to the minus 1. So it has to be much bigger, because again, these have to multiply out to equal 10 to the 14 because of the KW. Times 10 to the negative 14, okay? And again, when we are adding, when we're multiplying exponents, we're adding them, okay? So this is the scale, and again, the logarithmic scale gives us a much more intuitive interpretation of the concentration of H3O+. So what is the pH? I'll give you, so what is the pH of a solution, hydrochloric acid solution, that is 0.020 molarity? Since we know that HCl is a strong acid, it completely dissociates, completely ionizes to give H plus and Cl minus, okay? Because it's a strong acid, because it dissociates completely, we can use the pH calculation that I just went over. And again, in Chem 200, this will be way more, you'll dive a lot deeper into calculating concentrations of acidic and basic solutions. But again, for strong acids and strong bases, we know that they dissociate completely, so it's completely fine. So you're just going to take the concentration that you have here, that's equal to the concentration of H3O+, and then again, you're just going to take the negative log of that, right? So negative log 0.02, and essentially you just plug in your calculator, that's going to give you 1.70. What is the solution? What is the hydronium ion concentration of a solution with a pH of 5.2? All right. Again, since we have a solution of 5.2, and we know this is the reverse. Okay. So if we have a solution, pH is equal to 5.2, and we know that pH is equal to the negative log of the hydronium ion concentration, in order to solve for this, we're going to have to do the opposite of the negative. The opposite operation for log, which is taking, whatever here and raising it to the power of 10. So again, if pH is equal to 5.2, and we know, and it's already written here, but I'll just write it out, and we know that pH is also equal to the negative log of H3O+, okay, then if we have 5.2 is equal to the negative log of H3O+, okay, then what we're going to have to do is we're going to have to take the negative of this, and the opposite of a log is raising this to a power of 10. So it would be 10 raised to the negative 5.2. That's going to give you the concentration of H3O+. So here it is right here. So that's going to give you 6.3 times 10 to the negative 6 molarity. So if you want to calculate the pH of bases, so say you're given the solution concentration of hydroxide anions to be 10 to the negative 3, and you need to calculate, and you want to know what the pH of the whole thing is. The first thing you're going to have to do is you're going to have to understand that this equation right here, right? We have this, right? We have this. So we're going to first have to rearrange and solve for this, okay? So the way that you're going to do that again is obviously you're clearly going to divide both sides by the concentration of OH minus. So that's going to give you H plus is equal to 1.0 times 10 to the negative 14 divided by the concentration of hydroxide ions. This is this right here. When we divide, right? When we divide, we are subtracting. So when we're subtracting two negatives, we're essentially adding this to this. So 10 to the negative 14 divided by 10 to the negative 3 is going to give us 10 to the negative 11. Okay, so that is, again, that's the concentration of H3O+. So now that we have the concentration of H3O+, we can just plug that into our pH calculation and say pH is equal to the negative log of 10.0 times 10 to the negative 1.0 times 10 to the negative 11, which is, you can easily just say that's 11. So final answer, pH of a hydronium ion, a solution with a hydronium ion concentration of 1.0 times 10 to the negative 3 is going to be 11, and that is very basic. We will do this one in class, or when we meet for lecture. Again, we'll do that one as well. And then what we'll do is we'll fill out this scale right here, but you guys can do this stuff on your own. And that's it. We're done. I'll go ahead and stop. And we will meet on Tuesday for our final lecture, and then we have exams on our fourth exam on Thursday, and then review, and then a final the following Thursday. So thanks again, and I'll see you guys tomorrow, or I'll talk to you guys tomorrow.